Hello, welcome back to this video series on cryptography. In this segment, I'm going to talk about these two questions. The first question is about perfect secrecy and the size of the key space. Okay. In particular, if a crypto system is perfectly secure, the size of the key space must be greater than or equal to the size of the message space. Okay. The second question I will investigate with you is it possible to build a perfectly secret encryption scheme with shorter keys? Okay. Suppose you have a message variable, random variable m denoting the message. What is the probability that message takes a value m, given that the ciphertext variable c takes the value c? This is same as the probability of message being m. Okay, what it means informally in plain English is that if you observe the ciphertext, it gives no information about the plain text. No additional information can be gathered from the ciphertext. That kind of system is called perfectly secure system. Okay, so let's assume we are given an encryption system. We don't know how it's implemented, but we do know that the system is perfectly secure. Okay, and we would like to argue that the size of the key space must be greater than or equal to the size of the message space. So I'm going to prove this. So now we can apply Bayes' theorem as follows and think about perfect secrecy. So we do know from the previous equation that P of m by m, right? We do know this part. We call this equation 1, which is coming from the definition of perfect secrecy. And this is equation 2, which is from Bayes' theorem. Okay. If we compare 1 and 2 very carefully, we do see that this portion is over here and this portion is over here. Okay. That means this portion must be 1, right? And in other words, we can rewrite this as follows. Probability of C by C by m equal to m is equal to probability of C equal to C, which makes sense. Only if these two are equal, the numerator and denominator will cancel out, right? We can strike this portion and this portion, and now you get from 2, we can get back to 1. Okay, I hope this idea is clear. So because of perfect secrecy, we have other equation now. Now we can visualize this in a table structure. So I'm going to draw a table like this as follows. So you have a bunch of messages, right? We don't know how many messages are. Let's say M1, M2, and so on. Finite number of messages. Okay. We have a bunch of keys, say K1, K2, and so on. Okay. And we have ciphertext, say C1, C2, and so on. This table will be filled. This is according to an encryption scheme. We will be able to fill up this table. What it means is that you encrypt a message M1 using K1, you get ciphertext C1. Okay. And you may get some other ciphertext over here. All of the places will be filled with a bunch of ciphertext. Okay. Now let's take the first column. Okay. Let's fix the first column for a moment, which means we fix the message M. Let's say M is M1. Okay. M is equal to M1. We fixed it. What can we say about the column number 1? The column number 1 should have all the ciphertexts, okay, that are generated by the encryption scheme because of equation number 3. Equation number 3 says that if you know a particular message, right, in this case, we fix the message M to be M1. We cannot rule out any other ciphertext. All ciphertexts are equally likely to occur, right? How many elements are there? Unique elements are there on column number 1. That's nothing but the number of ciphertexts. Okay, all right. So what it means is now very clear that first we fixed the first column. We counted how many ciphertexts are there. We concluded there are C ciphertexts, right? That's the bar I'm putting in front is the cardinality, the set of all ciphertexts. All ciphertexts must be present as part of the first column. Otherwise, this equation 3 is not true. Okay, we are inferring that from the equation 3. Okay, which means that the number of keys, right? The number of keys K1, K2, and so on must be at least the size of the key space. Okay, why do I say that at least? Why not just say equal? The reason is that it is possible, for example, another key, say K3, also gives C1. It's perfectly possible, right? 2 different keys. When I encrypt message M1 using K1, I get C1. when I encrypt message M1 using K3, I also get C1. That's perfectly fine. So you can have more keys. That's the reason why we say K greater than or equal to size of the cyberspace. So we got the first inference from the definition of perfect secrecy. So let me call this as equation number 4. We still have to connect that to M, right? Okay. Now let's go row wise. Okay. So we definitely need, say, take first row, for example, K1 we encrypt with M1, we get C1. K1 we encrypt M2, we will get something other than C1. Okay. So if we count the number of columns this direction, right, it must be clear for you that the size of the ciphertext is greater than or equal to the size of the plain text, because there is no duplicate here, right? If you get C1 here, you will not see a C1 here. So it must be different, and it must match with every message that is on the top, right? Otherwise you would not be able to invert, right? That means that the size of the key cipher space must be greater than or equal to the size of the message space. This is true for any crypto system, not necessarily the one perfect secret, right? It's true for any crypto system. So now we combine equation 4 and 5. What we can confirm is that the number of keys, the key space, must be greater than or equal to the number of messages. Okay. This is one of the important conclusions we can draw if the crypto system is perfectly secure. Now we can start thinking about the second question. Okay, is it possible ever to build a perfectly secret encryption system with shorter keys? Okay, this answer is extremely easy now because we proved the first problem. Let's say it is possible. If it is possible to build a perfectly secret system with shorter keys, what can we say? I mean, it should not be possible. The reason is as follows. We are saying the negation of this part, right? We are saying this is violated. Okay, if this is violated, so now we go back to logic in discrete mathematics. If you have a proposition, say, I'm going to use a variable a. Okay, if a then b, right? Okay, what does this mean? This means that not b implies not b implies not a, right? The notation, what it means is that in logic, if this condition is violated, right, then this condition will also be violated. Okay, that means you cannot build, if a is a perfectly secure crypto system implies b, which is the size of the key space is greater than or equal to m. Okay, this is the logic statement we are given. That's equivalent to saying that not b implies not a. That means if this property is violated, right, then perfect secrecy cannot be achieved. Okay, so it directly comes from the logic notation, okay, from discrete math. So the conclusion is rather striking. You cannot build a perfectly secure crypto system using short keys. So what I wanted to show to you is that suppose somebody is saying that they build a system, say an encryption algorithm that takes a block cipher of length, say 128-bit, and the key size is just say 100-bit, and they claim it is a perfectly secret encryption system, then you can say that's impossible because we just proved it here, right? So you cannot build a perfectly secure encryption system which satisfies the equation 1, meaning this cannot be possible unless the key space is at least as large as the size of the message space. Okay. If you are using AES, for example, in counter mode or even in GCM with key size, say 128-bit, and message, suppose you are encrypting a 256-bit message, right? Now the message space is longer than the key space. That means it cannot be perfectly secure. That's for sure. Okay, that's all. Thank you very much for your attention.